hey, if you're up here at the roller coaster at the top, you're all PE. So let's say there's 10 joules. There'd be way more than that because roller coasters are so heavy and so high. But you'd have zero kinetic energy, and then the point of emphasis would just be as you go down to their lowest point, zero PE and then all KE. But notice when you add the PE and KE, it's equal to before and after because energy cannot be created or destroyed. So it always is going to sum to 10 joules. And then at the halfway point here, it's going to be 5 and 5. So I know it's not in the standard, but I would definitely talk about energy conservation here. Energy cannot be created or destroyed. The next one's a quick one. Develop models to describe the atomic composition of simple molecules and crystals. The first thing that popped into my head is if you took carbon and you can rearrange it in different forms to get graphite versus diamond. There's a lot of examples like that. I'm sure your book will have some. Develop and use a model to describe how the total number of atoms does not change in a chemical reaction. So we're into chemistry now. This is your good old fashioned. You got to balance equations. So I just gave an example. You're burning methane gas, CH4 plus O2, CO2 and H2O are yielded, and then you got to balance them out because you can't. It's kind of like a teeter-totter, right? Like you got to have the same number of atoms on both sides. And I would definitely point out the conservation of mass here, since maybe you've already talked about conservation of energy. You can talk about, oh, hey, what does it mean for things to be conserved? So you can conserve energy. You can't destroy it. You can conserve mass or matter. You can conserve momentum. Momentum gets transferred. So I like that word. And plus, when they take physics and chemistry later on, big ideas. Develop and revise a model to describe that when the arrangement of objects interacting at a distance changes, different amounts of potential energy are stored in the system. That's a tough one. I think an easier way to show the different amounts of PE could be stored is the good old take a ball bearing on a ramp, and you put it at a small height and let it roll down the ramp and then measure. Maybe you do like 10 trials, see how far it rolls, double the height, and then have them make an observation about what's going to happen there. And should be about twice as far because it has twice the energy. So I think this is a pretty tough standard. I'm revising a model. But I think this is a good first attempt for our first year teaching physical science at the middle school levels. This standard is interesting because so far we haven't done much with light and waves, and all of a sudden we got a wave standard here. It says develop and use a model to qualitatively describe that waves can be reflected, absorbed, and transmitted through various materials. So this is going to be probably at the end of your waves unit. Maybe you did sound waves, now you did light waves. And basically you're going to have to talk about, you have light and white light. This is, let's just say this is the sun, which gives off mostly white light if you're in outer space. White light is Roy G. Biv, right? All the colors make up white light. And then you're going to talk about it. And even when I taught high school physics, even honors physics, this was a confusing topic sometimes because they kind of double think it. But if you have white light shining onto what is a red book, the reason the book is red because it reflects red and absorbs orange, yellow, green, blue, indigo, violet. So this would be considered an opaque object because light cannot transmit through it, not even partially. So the color that you see is the color it reflects. So if you see a blue object like somebody's blue shirt, it's going to reflect blue and absorb the rest. That gets a little confusing when you talk about what are called transparent objects. A good example of transparent, these are awful sunglasses, but these are blue lens sunglasses. So basically you can picture some really cool person wearing blue lens sunglasses. If you had white light from the sun, the Roy G. Biv, red, orange, yellow, green, blue, indigo, violet, the only light wave that would go through these blue lens sunglasses would be blue. So that's why everything has blue hues to it. So basically, blue's transmitted through, without the voice crack there, blue's transmitted through, and then all the other colors are absorbed into the lenses. So this would be considered a transparent object. So you get reflected when you have light reflecting off like an opaque object. Both, you can talk about absorption, and then transmitted would be transmitted through what's called a transparent object. Cool? Yeah, that one comes out of nowhere, really. It's like we're talking about balancing equations. Let's talk about PE. Let's talk about waves and light waves. But all right, we're getting there. Construct an explanation based on evidence for common phenomena that can't be explained. That can be explained. By the motion of molecules. So basically, motion of molecules. I start to think about phases of matter. I just thought to myself, the other night we made spaghetti. So a good example: you have water as a liquid, you put energy into it. Maybe you leave the top to the pot on, and you could ask them, why does it do that? And then, because it says construct an explanation, it's important to make them construct it, right? The one that gets us up in Minnesota is maybe around November, whenever it starts to get cold. A lot of students, and maybe not so much with 8th graders now, but back in the day when it was 9th grade class, you might have some students starting to drive. They might notice their tire pressure lights come on in their car. And maybe just ask them, hey guys, I was driving to school, my tire pressure light came on. Anybody want to make formulate a hypothesis to why that happened? And as it cools, right, your molecules slow down and it decreases pressure. So in the wintertime, the tire pressure light comes on. The next benchmark here, construct and test a modified device that either releases or absorbs thermal energy by a chemical process. I think that's a lot of words to say you're looking at endothermic versus exothermic reactions, and that's probably a topic in your book. So there's probably lots of examples. I do want to skip ahead to this next one, which is a good physics one. Not that that's not a good chemistry one. But design a solution to a problem involving the motion of two colliding objects using Newton's third law. And so teaching honors physics for many years, this is the example that I would give, but it's plenty okay for middle school science. I would put up an image of a small, like, mini car versus a big truck, and I would say they get in a head-on collision. Which experiences the greater force, the larger force, and then I'd let them talk with their neighbor, like a think, pair, share. But the thing that's interesting about this, Newton's third law, notice there haven't been any standards that said what's Newton's first law, Newton's second law. So I just wrote at the bottom, Newton's first law is the good old objects at rest stay at rest, objects in motion stay in motion, unless acted upon by an outside force. The second law is F equals ma, which is our math one. That's going to give us some math. And then the third law, which is the one that this one's talking about, for every action, there's an equal and opposite reaction. So the answer to this question in red is they actually experience the same force. And here's the reason why. So Newton's second law says that F equals ma. Well, this truck is very big. So to kind of graphically show this, I'd say it has a big mass. When it hits the small car, though, it's not going to move very much. It has a small acceleration. So I'd make my acceleration really small. On this side, I would say this car over here has a really small mass. So that means that when it hits the big truck, its acceleration has to be big. Because according to Newton's third law, for every action, there's an equal and opposite reaction, which means the force is the same. But here's the deal. The force that acts on this massive truck means it doesn't accelerate very much. And then the force that acts on a really small car means it's going to accelerate a lot. And then just an extreme example, I'd say, hey, what if a little bug was flying through here and a bug hit that? Well, that has a really small mass, so it has lots of acceleration. And that leads into, well, why does the bug die? Well, it's accelerations that cause damages. So the acceleration being so big, if you're in a really small vehicle, you're going to have more damage to your car. So this is a huge topic that basically looks at Newton's first, second, and third law. So, yeah, I like that one. All right, we just have a few more here. Design and test the device that either minimizes or maximizes thermal energy transfer. Maybe somebody can post this, but a good old-fashioned keep the heat contest. You have different containers. They get to decide, or maybe they get to buy different things to try to keep their water, keep the heat the longest. That's a nice one for that. Construct and present arguments using evidence to support a claim that gravitational interactions are attractive. Basically, there's the different types of forces, gravity being the weakest of the four. But the one I like for this, you just take a mass and put it onto a spring scale, and you can see the mass always has weight acting down. It always pulls down on the spring scale. There's never a case where you'd hook a mass onto a spring scale and it'd push up. And then you can kind of tie back to when you talked about electrostatic forces. If you have a positive and a negative, you could have those be attractive as well. So they can attract, just like this object is attracted down towards the Earth. But electrostatic forces can also repel. So when you talk about charges, you talk about magnets, you get attraction and repulsion. But gravity or gravitational forces, you only get attraction. Things are attracted to the center of our Earth. All right, compare and evaluate evidence to support the claim that when kinetic energy of an object changes, energy is transferred to or from an object. This one, good old-fashioned Newton's cradle. Newton, you're going to have to talk about momentum at some point a little bit, even though it's not in the standards. But if you pull one of the spheres back, that's going to have kinetic energy associated with one sphere, so one comes out. but then also pull 2 back and see that sure enough 2 come out. And then you can really blow their minds, because if you pull 3 back, you can say, well guys, we pulled 1 back, 1 come out, pulled 2 back, 2 comes out. What if you pull 3 back? Well, that kind of causes a little cognitive dissonance there, because you get pulled 3. How many should come out? Well, you'll surprise yourself, and it's cool, record it in slow motion. But if you have a good Newton's cradle, 3 come out. So you pull 3 back, 3 have to come out, because energy cannot be created or destroyed. Cool. And then you can do the thing where you pull 1 back at the same time, and you can see it just kind of, yeah, have fun with that. All right, this next one, we go from doing some good physics ones to a good chemistry application. Gather and evaluate information from multiple sources to describe that synthetic materials come from natural resources and impact on society. The first thing that popped into my head is back in the day, I used to do a little unit on, you take crude oil and you refine it. And when you refine crude oil, you heat it to different temperatures, and you can make these different hydrocarbons that come from crude oil. And especially back like 10 years ago when gas prices were super high, you could talk about, well, how did gas prices affect prices in the store? Well, it all comes from crude oil. And if crude oil is expensive, it's going to affect the cost of gasoline, which affects the price of oil, which affects the price of plastics. And so I imagine that's what they're talking about, the impact on society and natural resources. Crude oil is a natural resource. Of course, after talking about hydrocarbons, we'd go to this last one. It says, integrate qualitative scientific and technical information to support the claim that digitized signals are a more reliable way to encode and transmit information than analog signals. I would say, where'd this one come from? It's a good one, though. This is basically going to be somehow tied into when you're talking about waves. And then you probably talk about sound waves and go to light waves. And a good example for this is when you're on your phone and you're talking, that is a sound wave. So in between your lips and the phone is a sound wave, which would be considered an analog wave. Cool? Now what happens is your phone then takes it and encodes that analog wave into a digital signal, and then your phone transmits a radio wave. And when you say radio wave, your students always assume that that is a sound wave. It is not a sound wave. So this radio wave is an electromagnetic wave, and this travels at the speed of light. So basically your sound wave is traveling at about 340 meters per second, and this travels about 1,000,000 times faster. So what happens is it's digital signal. It's more reliable because your sound wave wouldn't travel very fast to get to the cell tower, right? And then that cell tower has to relay it to your friend. So you can talk about sound wave gets encoded to a digital signal in here, goes to a radio wave, goes to the cell tower, which looks like this, and then that cell tower relays it using an EM, electromagnetic radio wave, and then your cell phone for your friend, it takes it and it reverses it back, and I draw like a little notes like this to a sound wave that you can hear. And then I talk about why would you not use sound waves? Well, sound waves travel 1,000,000 times slower than light waves. So that's why you can talk to somebody on the other side of the world, because light waves travel at 186,000 miles a second. So that's why it's definitely a better way to encode it digitally, have it send as a radio wave, and then it get relayed. I kind of talk about maybe if you're at a sporting event, you can hear a sound wave, like there's a delay, like maybe somebody gets hit at a football game and you hear the hit, you see it before you hear it. Well, I'm like, well, gang, that's at a football sporting event. You hear a delay. Imagine if you're trying to use sound waves to transmit your phone call around the world, it'd be so slow. So we use light waves, EM waves. That's a quick crash course on all the standards. The good news is we went really fast. There's only 22 standards. Kind of if you total up how I broke it up, there's 12 physics, 10 chemistry. So 45% of your year may be chemistry, 55% physics. I'll be honest, I tend to have taught physics more. So I'll probably, when I'm teaching this, I'll say 2/3 physics my first year, I'd imagine, and 1/3 chem. And then my goal would be to balance them off. But I hope this is just the first step, and then we can go from here and maybe get some cool projects linked in here. But I hope this helps. I hope that the night before you're teaching something, you can look back here and be like, oh, maybe Travis Laurent gave me an idea or something to think about. But all right, and feel free, please share this video with other people who you feel might be struggling. We want to help everybody out. All right, good luck this year.